think it's recording. Let me see. It says it's recording down there. I want to pull this up there just so I can kind of. Yep. Okay. So it is recording. So like I was saying, we kind of went through and proved this yesterday, and talked about its implications. And so what Rachel, what you were saying, kind of really leads into the next kind of final theorem, which is that if a vector field, or if a line integral is independent of path, then we can absolutely show that that is a conservative vector field. Okay, so in other words, if it's independent of path, which we know we can show by showing, for example, if all closed loops go to 0, then that means it's independent of path. And so, but if it's independent of path, then we know absolutely that it's a conservative vector field. Okay? So I want to go through this proof, and it's actually it's a little technical, but it's really kind of a brilliant use of abstractness and kind of generalities. Okay, so we actually are going to start off by defining this function f. So we want to show that this function f exists such that the gradient of f is our vector field, and so we can actually start off by defining it. Okay, so we're going to let a what's called a be. So this is just going to be a fixed point. In our region B. Okay, so A is just kind of some point in space, and we're going to define our function f of xy as the integral along C of FDR, where C just goes from our fixed point AB to some floating point xy. And so xy can be anywhere in that region, and f is going to be the line integral from our fixed point to that point. Okay? Does that make sense? So C is just some curve between AB and xy. Okay, so let's kind of take a look at this. So if we have some region B in space, and we maybe pick here to be our point A, or point AB, and then we'll say xy to set here. Okay, and because this, our assumption here is that this vector field is independent of path, then it doesn't matter the path we use to get between these two points. Okay, and so kind of, for example, we can cook up kind of whatever path we want. So that could be a C, or we could simply taking a straight shot, and that could be a C. And so how we're going to prove this is we're actually going to pick kind of two specific C values, or two specific curves, and kind of set them equal to each other, because we know that it's going to go, the integral is going to be the same either way. Okay? So, what I mean by that is, we're going to kind of assign this circle around our point, and we're going to think of making this curve C that's going to maybe approach, and then right as it gets into the circle, it's only going to approach this point vertically. Okay, so we have C1, which is whatever curve here, and then C2 is just going to be that vertical segment from this point here in our circle up to our point xy. Okay, and because this is a vertical segment, we know that this point down here is going to have the same x value as this point up here. It's going to have a different y value. So this is also going to be x, and we'll just call this y1. Okay, so we kind of called this whole curve C, and the way we define f of xy was the integral along C, which is going to be the integral along C1 plus the integral along C2. Okay, and so if we want to switch to our parameterization, and again, we can be pretty general about this because we don't really we haven't really defined a specific curve for C1. So we can just kind of say that C1 is parameterized by some vector function R of T. Okay, and so what this would look like, then this is just going to turn into the integral from AB up to x, y, comma 1. And then this is going to turn into the integral from x comma y1 to x comma y. Okay, and so we're almost kind of to the point where we can really start seeing what's going to happen here. What I want to do, what I want to kind of think about is the other way we can write out like these line integrals. So remember we saw, aside, that if f equals t, with the I component is some function t, and the j component is some function q, then we saw that the line integral over f was equal to the line integral of p dx plus q dy. Does everyone remember seeing that? Okay. So what we want to do is kind of rewrite this one more time. Okay. So kind of here for this funny looking equation. What in the world can we do with it? sort of. You're on the right track. Do what? No, they're functions. Yeah, they're functions. Okay, so not quite. So, but what we can do is, and this is kind of one of these brilliant tricks of analysis, is when you want to get rid of something, you think of you look for things that are constant with respect to maybe one variable or the other, because if we differentiate, that'll just go away. And so what I mean by that is if we take the derivative with respect to y of this whole piece, does this at all vary as y? This y over here varies? Because notice this goes between some fixed value b in the y direction to some other fixed value b in the y direction. No matter where x is, it's going to go to, wherever xy is, it's going to go to xy1, and then the last little bit is where it's actually going to go to that y value. It might go up or down. Okay, so if we differentiate with respect to y, this whole piece here is just going to be 0. Okay. And so here we would have the derivative with respect to y of this benefit. Okay. Okay. Now, we have to make kind of one more observation. And this is the whole reason we defined our region here, or our curve here, to be this vertical line segment right at the end. Because A, it makes this integral here be totally constant with respect to y, and so when we differentiate with respect to y, it goes to 0. And it also allows us to evaluate this integral here really easily, because this is just over C2, which is a vertical segment. And what's true? Do we know anything about dx or dy over a vertical segment? If it's totally vertical, is there going to be a dx? So here, this tells us that dx equals 0. And so what we end up having is df dy equals the derivative with respect to y of the integral q dy, and the derivative of the integral, well, that's just going to be that function here. Okay, so what that tells us is that df dy equals q. And so you might be thinking like, why in the world does that help us? Okay. Well, if we, I'm going to kind of rewrite that up here. df dy equals q. And if we kind of repeated the same process, let me see if I can snag this stuff. I want a circle and a point. I don't want a curve. Right, that's exactly what I want. Okay, so because of path independence, we can define another path that would accomplish the same thing, and it would be the same integral. And the way we would do that is we would have some curve C1, and we would come to right here, and then the last segment would be perfectly horizontal. So this would be x1, comma y, and we would go over to xy. And so we would define the same thing, except on this new curve C, and we would differentiate, instead of differentiating with respect to y like we did there, we're going to differentiate with respect to x, and we would kind of go through the same process. The first piece, because this over C1, that doesn't depend on x at all, because it's between two fixed points of x. So that would go to 0. And this last piece, it doesn't change at all with respect to y. So we would kind of cook down to where we have df dx equals the derivative with respect to x of the integral just over that last piece, which is from x1y up over to xy of t dx. And what that tells us then is that df dx equals t. Okay? So, in other words, f, which equals ti plus qj, well, that equals the gradient of f with respect to x, I, plus the gradient of f with respect to y, j, and we recognize that. That's the gradient. So that completes it. And so, the whole thing then goes back to, if it's independent of path, then it's a conservative vector field. And we can just kind of use those two components, the p and the q, as those are going to be the components of the gradient. Okay, so kind of the big implication, in other words, is that if f is independent of path, which would again mean all closed loops go to 0 or anything like that, then we have this equality right here. Okay, but there's still kind of like one last question, which is, if we know what the vector field is there a way that we can guarantee that it's going to be conservative? It's like we're given an explicit formula for the vector field. Can we do like some kind of test to see if it's conservative? And it turns out there's actually a pretty convenient way we can do that. So this equality tells us that df dx equals p. And so if we differentiate this with respect to y, then we would have d squared df, dy dx. And that would be equal to the derivative of p with respect to y. Okay, but we also know that df dy equals q. And so if we differentiate this with respect to x, then we're going to have the derivative of q with respect to x. And so what does that tell us? What do we know about those two are equal? Yes. So remember, if they are continuous, if the I are continuous, if they are continuous, then these two are equal. And so that tells us that dp dy has to equal dq dx. Okay, so in other words, we take the ith component, we take the x component of our vector, p, and we differentiate with respect to y, and we take the y component of our vector, q, and differentiate with respect to x. And if they're equal, then it's going to be a conservative vector field. And so that actually is a proof for this theorem. So if this vector field is conservative, then this is true, which tells us kind of conversely if this is not true, then our vector field F is absolutely not conservative. You know, so in other words, this is like kind of if A, then B, and so therefore if not B, then not A. If something is a square, then it is a rectangle, and so therefore if something is not a rectangle, it can't be a square. You know, and so this is kind of the same thing. So if this fails to be true, then we know it's not conservative. Yeah, like the second derivative test. Yeah, no, it's not. It's not quite like that. If we want to kind of, if we want to see, you know, for this to guarantee that it's conservative, like, you know, because that's kind of what we would like to be like. Okay, we apply this test, we get that these are equal, therefore we know it's conservative. We can't quite do that without imposing a little bit of a restriction on sorry, the converse is more than the inverse, but whatever. So we have to kind of impose a slightly stronger restriction on D. So here we just said that D was, we just kind of said it was a domain. I think we mostly are concerned with open, but for, for the, in order to define this region, you know, in order to define the converse, we have to say that D is simply connected. Okay, and simply connected is pretty straightforward. So a simple curve would just be, you know, any curve that doesn't intersect itself and it's closed. So it's closed and no intersection. And so, you know, for example, if we had like something like that, this is not a simple curve because it intersects itself. Or if we had a curve, maybe that was like, this is also not simple because it's not closed. Okay, so it has to be both closed and no intersections for it to be a simple curve. And then from that we can define a simply connected region, which is just one where every simple closed curve only has points that are in the region. And what does that really mean? It has really what it comes down to meaning is there aren't any holes in the region. So if we take just a region like this, then any simple closed curve only contains points that are in the region. Okay, whereas if we had a region here, maybe that has a hole in it, then we can construct a simple curve that has points that are not in the region. Okay? Do what? An eyeball with like funny looking iris. And these are. I see compact there with lashes. He's got an eye. He's got an eye with his eyelash. So that's kind of the difference between connected and simply connected. Another kind that would fail to be simply connected would be something, if we just had a break in it. Because we could cook up plenty of curves that would enclose points that were not in that region. Okay? Okay. So if we define our region like that as a simply connected region, then we can kind of also say that if these partial derivatives are equal to each other, then f is conservative vector. Okay, so this is kind of, before we had if not b, then not a, this says if b, then a. So in other words, on a simply connected region, these are like if and only if statements. If it's conservative, then this is true, and if this is true, then it's conservative. And this, these are kind of our goals, because the whole thing is we're trying to figure out ways to find a good test to see if a vector field is conservative or not. Because we know if it's conservative, all closed loops go to 0. Line integrals, we don't have to worry about the path. All we have to worry about is the endpoints. And so getting to being a conservative vector field is kind of what we want. Okay, so I think I just want to go through a few examples of how we can put this to use. Okay, so at first I just want to go through a couple of examples of determining whether or not a vector field is conservative. Okay, so with this one, our p function is x minus y, and our q function is x minus 2. Okay, and so remember the test is we take the derivative of the kind of first component with respect to y. And so dp dy would be what? And then dq dx would just be 1, and so it's not conservative. because those are unequal. And so, yeah. Not conservative. So it's a liberal vector field.
Not conservative, bro. They approved it.
It's a moderate vector field. It's so funny how in like not all times, but almost all times in American politics, up until this point, like being a moderate has been like what gets you elected, and now like any compromise or moderation, you barely gonna be able to hold on to your Senate seat. Or, you know, like Romney, people are terrified of Romney because he's a moderate. And, you know, and a lot of people were disillusioned by Obama coming into office because he was doing really well, and then he came into office and he became a moderate. You know, it's like, yeah, he's a pragmatist. It's like this is how we can get things done. So
With all the presidents, you just laugh. I'm scared.
yeah, I would do it.
Ah. You guys get like it. You're scared of us.
So are these equal? Is this vector field going to be conservative? So this is going to be 2x, and this is going to be 2x. And so the region, because this doesn't tell us what region we're talking about, the region D is going to be the entire real plane, which is open and simply connected. And so because these are equal, and because we're talking about an open, simply connected region, therefore S is conservative. So, you know, that's really the whole test, is just checking the partial derivatives. But now kind of the question becomes, well, what can we do with that? How can we, if we can show that it's conservative, can we come up with the function? Can we look up the function whose gradient is this vector field? You know, because we know that this vector field is conservative, which means that it's the gradient of some function. And so we just want to know, like, can we cook up that function? And so let's kind of let's take a look at an example of how to do that. Okay, so we already know, this is the one from the last example, and we know it is conservative. So we know that there is some function that, or as there exists some function f such that f, gradient of f equals our vector field. And we actually kind of already got a hint from how to do this. Because remember, we had that equation where f equals pi plus qj, and it also equals the partial of f with respect to xi plus the partial with respect to I or y j, because it's just a gradient. Okay, and so we get these two equalities from this. So we know that df dx equals p, which is going to equal 3 plus 2xy. And we also know that df dy equals 2, the thing was x squared minus 3y squared. Okay, so how could we use these to figure out what f is going to be? That's all we got to do. So we got to integrate this one with respect to x, and this one with respect to y, and then compare. Okay, and I'll show you what I mean by comparing in just a second. So when we take 1, let's call this one 2. When we take 1 and integrate it, we're going to get f equals 3x plus x squared y, and then plus some constant because we integrated. But that constant could be a function of y because we just integrated with respect to x. Okay? And when we integrate 2, we're going to get f is equal to x squared y minus y cubed and plus some other constant function. Maybe we'll call it L. And that's going to be a constant function of x. Because when we differentiate with respect to y, this would fall away. Okay, so can we kind of, by comparison, can we figure out what f is going to be? Notice, we know that this is going to be in here. And then this, well, that's a constant, that's a function of y, so that would be a constant with respect to x. So this negative y cubed could serve the purpose of that function, constant function there. And likewise, this 3x, well, that could be our function, our constant function with respect to x. And so all f is going to be is 3x minus y cubed plus x squared y. So, and we sneaky, and we also, kind of we kind of also need to add that constant to the for technicality's sake, but yeah, the square. So we're done. So that function, and we could go through and confirm absolutely that if we take the derivative with respect to x, for example, we're going to get 3 plus 0 plus 2xy. We got 3 plus 2xy. And if we take the derivative with respect to y, we're going to get negative 3y squared plus x squared, which is x squared minus 3y squared. So that will absolutely do it. Okay, let's look at one more example. This one is in, oh wait, we actually didn't finish that. Sorry. So we also want to evaluate the line integral. Using this, evaluating the line integral becomes really easy. Okay, so for part B, we want to evaluate the line integral over C of FDR. And I think we said C is given by RT equals ET sine T, ET cosine T from 0 to 5. So RT equals ET sine T, ET cosine T from 0 to 5. Okay, so how can we evaluate this integral? How will knowing this function help us? What if I do 1 quick 3 right? What is this whole thing equal to? Not quite 0. That's only the closed loop. Not quite 1. But y'all are on the right side. What is this only going to depend on? What part of it? The endpoint. So remember, this is the fundamental theorem for line integrals. And so all it's going to be is f of b minus f of a, which kind of, in our case, would be f of r of phi minus f of r of theta. And so we don't have to worry about doing this crazy, nasty line integral. All we have to do is do a little bit of algebra with our function. Okay? So what would r of pi be? So I think it would be 0 e to the pi? Or it'll be negative e to the pi 1. Because sine of pi, cosine of pi is negative 1. Yeah, so it'd be 0 and then negative e to the pi. So this is going to be f of 0 negative e to the pi minus f of, and I think it's going to be, so yeah, it'll be 0, 1. Okay, and I already forgot what. So it's 3x minus negative e to the pi q plus x squared y plus 0 squared negative e to the pi minus, when we evaluate it, we're still going to have 3, 0 minus 1 cubed plus 0 squared times 1. And so I think it's just going to be equal to e to the 3 pi plus 1. Just like that. So now, this is getting worse and worse. Okay? So this, we kind of highlighted the technique for figuring out what the gradient function is going to be. And so it's going to be the exact same in 3, or if we wanted to do more dimensions, we could. But we're kind of, the process is going to be the same. And so what I mean is that the f dx is still going to be kind of our first term, our p, and the df dy is going to be that q term, which is going to be 2xy plus e to the 3z. And df dz, which would be the third part of the gradient, is going to be 3y e to the 3z. And so the only difference is that instead of having 2 equations, we're going to have 3 equations. Yeah, and so each of those constants could be a function of 2 variables. So what would, based on 1, what is f of x going to be equal to? Or what is f going to be equal to? Yeah, so it's just going to be xy squared plus, yeah, so I'm going to use f, and that's going to be a function of y and z, exactly. And then 2 is going to be, if we integrate with respect to y, we would get xy squared again from here, and then this would be y e to the 3z. Because that's just constant with respect to z. And then we would still have another function here of x and z.
unless I could do that.
And then from 3, that would tell us that f equals y e to the 3z
Plus some function of x and y.
Okay, so notice. So we need this function that depends only on y and z. And so do we have a piece in here that would fulfill that? So that would be like this piece here, y equals 3z. And then what about, we also need this h of xy, and that would be the xy squared. And so then g of xz would just be 0. Or, or we can think of it as being that constant. If we don't have to force any terms that aren't going to, because this would have shown up here if it depended on x. It would have been in that partial with respect to x. And it would have showed up down here with z if it had depended on z. And so that tells us that this thing didn't actually depend on either. And so it was just kind of a constant. And so our final function f, let's go on the highlight. Our final function f of x, y, z is going to be xy squared plus y e to 3z.
Close enough.
Okay. So that's it for the fundamental theorem. That's kind of that wraps it up. And so I would like very very briefly, just kind of as an aside, to talk about how this relates to conservation of energy and how we can kind of think of what this has to do with a conservative vector field. Okay, so what I mean is that we know that work is defined as the line integral all along the curve C. But we also know, but we also looked at the fact that force equals mass times acceleration, which equals mass times r prime of t, where rp parameterizes c. That's true. I can spell that different every time I read. But that's okay. And so we can. Sorry, this is actually going to be the second derivative because it's acceleration. So remember, r prime of t is going to be v velocity. R double prime of t is going to be acceleration. And so we can rewrite this work as m times r prime of t, and then we can dot that, because we know dr is really like r prime of t dt. Okay? And so, being that we have written everything in terms of our parameter t, we also can switch to our our bounds on T. And if we pull this M out, what we have on the inside is R double prime of T dotted with R prime of T. And I don't know if you recall from way back in the day, my way back in the day, I mean, a couple weeks ago, a couple months ago now, we saw that if you take the derivative of the magnitude, I think it's actually the magnitude squared, yes. Yeah, it was. You take the derivative of the magnitude squared, then this equals 2 times R prime of T dotted with R double prime of T. And so if we divide everything by 2, then we see that we have exactly this right here, because the dot product is commutative. And so this work then is going to be equal to max over 2 times the integral a to b of d dt r prime of t squared dt. Okay? But we have the integral with respect to t of the derivative of a function with respect to t. So that's just going to turn into evaluating that function at our endpoint. So we have m over 2 of d squared minus m over 2 r prime a squared. Okay, and so if I just rewrite this using kind of our notation, this is just the velocity, and this is just the velocity. And so this rewrites as 1/2 m times v squared minus 1/2 m v squared. Does anyone know what 1/2 m v squared is?
Oh, is that,
Not quite momentum. So kinetic energy is equal to 1/2 m v squared. And so what this says is that the work is going to be equal to the kinetic energy at B minus the kinetic energy at A. The amount of work done is the amount of the difference in kinetic energy. Yeah, that's Einstein. That's just energy. That's the more general energy. Okay, so we have this equation right here, and then what I want to do is we also kind of assumed that this was a conservative vector field. So we know we can write it as the gradient of some other function. And so what we're going to do in physics, we actually take the negative gradient of the gradient, and we call this the potential function. The potential function. And the reason that we call that the potential function is actually because it gives us the potential energy. Okay? So, we know that work is also going to be equal to the line integral of C dr, but we can write that as negative times the line integral of this potential function dr, by the way we define that potential. And then we can use the fundamental theorem because this is a gradient, and so we're going to have negative P of P minus, because remember these are just, again, the endpoints. And so what this says is that work is also equal to the loss in potential energy. So before, this is the gain because we are taking the difference from the beginning. So this is like the gain in kinetic energy or the loss in potential energy. Okay? And so the whole big point of this is that if we take the negative ones and add them to the other side, so then we're going to have the kinetic energy at the end plus the potential energy at the end is going to be exactly equal to the kinetic energy at the beginning plus the potential energy at the beginning. So this is the total energy at P equals B. And this is the total energy at P equals A. And so it tells us that energy is conserved. There's no net loss in energy or gain. But whatever you start with is what you end with. And the whole thing about physics is that, mechanics is all about energy shifting back and forth between kinetic and kinetic and potential. And what this tells us is that if we're talking about a conservative vector field like gravity, like electromagnetic force, anything like that, then energy has to be conserved. So, that's that.